So, well, let's start now with the second part of this morning session. We are grateful to have Professor Johann Marton from the Stefan Meyer Institute from Vienna. So please, Johann, go on.
Thank you so much. So it's a pleasure to be at least online in this meeting. So that's a 10th conference on quantum foundations, taking place in Buenos Aires. Unfortunately, I cannot be there. It's we have in a full lockdown in Austria, and so I want to give you some information about our experiment in Gran Sasso. You can see my pointer here.
Yes, perfectly.
Okay, so here you see the surrounding of our experiment in Gran Sasso. And okay, so not going on.
Perhaps if you click on the screen, yeah.
So, yeah, okay, I'm coming to the outline of my talk. So the Pauli Exclusion Principle, as you know, is a solid pillar of quantum mechanics. It's a very robust rule. The question is, what is the reason for this Pauli Exclusion Principle? So even Pauli could not answer this question. And the other question is, are there really no violations? So first, it's connected with a periodic system of the elements, was a starting point. And also it's connected with the stability of matter, with the stability of neutron stars, and also some point has to do with quantum gravity. Okay, so we have, we want to, with high accuracy, an experimental test of the Pauli Exclusion Principle. So I will explain some methods for testing the Pauli Exclusion Principle, which were already done by others. And recent improvements of our experimental apparatus I will show, and results obtained so far. And then I will summarize and give a brief outlook. Okay, so here you see the collaboration of the VIP2 experiment. Mainly the participants are coming from Italy, some from Austria, France, Germany, Romania, and Switzerland. Okay, so Pauli in 1925 said, in an atom there cannot be two or more equivalent electrons for which the values of all four quantum numbers coincide. If an electron exists in an atom for which all these numbers have definite values, then the state is occupied. So this was published in a German language, Zeitschrift für Physik, in 1925. And the question is what Pauli is meaning with four quantum numbers, because the spin was not known. So Pauli was also named the double phaseness of the electron. So it was pointing in the direction. Okay, so these are Zeitschrift für Physik, and you see here Pauli was also sometimes in sport, beside his theoretical work, using a slide, and also with Niels Bohr, he was discussing the angular momentum. But spin is more than that. So it's classically not describable double phaseness of the electron. Okay, so the Pauli exclusion principle is intrinsically connected with the spin. So if you look in the handbook for students, it's saying spin statistics theorem is giving immediately rise of the Pauli exclusion principle. Okay, so in Ralph Kronig was a student of Pauli. He suggested that electrons have spin. Funny, in the same year as Pauli formulated the Pauli exclusion principle. And Pauli was not so impressed by this idea. and said it's indeed a not very clever idea. It's a very clever idea, but has nothing to do with reality. So Pauli actually changed his mind afterwards, but our knowledge today is that we have only bosons and fermions. So the symmetric states are related to bosons and the antisymmetric states to fermions. So here you can only one particle per quantum state. And these two bosons and fermions obey to different statistics, as you know. So the real discovery of the spin was done by Gaudsmit and Uhlenbeck. Unfortunately, they did not get the Nobel Prize. That's an interesting fact. And okay, our knowledge today is we have only bosons and fermions. And both sides are very interesting. So fermions are leptons, quarks, baryons. They belong to the class of fermions, and bosons are carrier of bosons and carrier bosons, so W's and Z, and mesons, so two quark states. Okay, so the general principle of quantum theory do not require that all particles are either bosons or fermions. The restriction comes from a postulate by Messier. And so then the bosons and fermions are separated. And there were several attempts to violate the spin statistics. There were attempts like parastatistics, so was leading to a large effect. This was ruled out. Then Ignatieff and Kuzmin so gave negative squared norm states and so on, the Q theory, space-like commutativity phase and so on. So every problem is weak points. So, and the test of the Pauli exclusion principle also is leading to negative results, and that's why we are pretty sure that it's a fundamental rule of nature. So all the proofs are negative proofs. So no single experiment could provide a positive signal of a Pauli exclusion principle violation. It's, by the way, it's the same like in the CPT case. So in the combined symmetry CPT, also up to now, there's no violation. And actually also this CPT theorem is going back to Pauli. Okay, so Pauli wrote this famous paper in 1940. It was published, The Connection Between Spin and Statistics. And it had about 200 citations, which is not very many citations for this important paper. But at that time, it was not so popularized. Today, there would be maybe thousands. So also it was discussed what Pauli principle has to do with the stability of matter. It was, for instance, review of modern physics. And also Dyson, he investigated the case. So without the Pauli principle, we show that not only individual atoms, but matter in bulk could collapse into a condensed high-density phase. The assembly of any two macroscopic objects would release energy comparable to that of an atomic bomb. So it was realized that it's, from the very fundamental point, the Pauli exclusion principle is also responsible for the stability of matter. Okay, coming back to models violating the Pauli exclusion principle, I only want to point to these models by Ignatieff and Kuzmin. They were introducing Pauli violation with a factor of beta. So this two state is forbidden, and then you get the probability for Pauli exclusion principle violation with beta square half, which is commonly used in the literature. Okay. And okay, so several proofs exist in the context of quantum field theory, which differ in clarity and the quality of physical insight. So I want to show this proof by Lüders and Tumino. They laid out a very clean set of assumptions in their proof in 1958. So, and especially interesting is the relation to the Lorentz violation, or Lorentz coming to the Lorentz group. So because this Lorentz violation is also searched for in many experiments now, even with antimatter and so on. And but up to now there's no positive signal for that. But you see here the assumptions they included, and maybe the best candidate would be a violation of the Lorentz symmetry. Okay, so Messier-Greenberg set up a super selection rule. So in a closed quantum system, you cannot expect that it will change from the initial state to the final state with a Pauli exclusion principle. So you have to, according to Messier-Greenberg, you have to use open quantum systems. So you have to introduce some new fermions to test the Pauli exclusion principle. Okay, so I wanted only to show that the proof of the Pauli exclusion principle in theory is not simple, already pointed out by Pauli himself, and the experimental tests of the validity limits of the Pauli exclusion principle are complicated and based on different assumptions for specific systems. Okay, so experimental tests, there is a broad variety of tests. So it was tested in atomic transition. That is also the region where our experiment is sitting. Then tested with nuclear transition, nuclear reactions, Pauli exclusion principle forbidden nuclear structures, atomic structures which are forbidden, neutrino statistics, and astrophysics and cosmology. So some of these experimental tests give a pretty high limit, but we want to go beyond these present limits. So what are the requirements to do a Pauli exclusion principle violation test? So we need a large number of fermions probing. We have to figure out the characteristic X-ray signal for a unique indicator. We have to use in the experiment very good energy resolution and a high efficient X-ray detection. It's clear because the effect, if it is there, then it's very small, and also low background. Also, like also all the low counting experiments, it's done in a low background environment. So, for instance, underground lab like Transasto. Okay, so here you see some beta square half limits obtained with atomic transitions. So the first one was by Goldhaber and Scharf-Goldhaber is 5, was leading to a limit 10 to minus 2. At that time, it was not clear if the beta decay is normal electron decay or can be something special and violating the Pauli exclusion principle. And then there were other experiments. So the prototype of our type of experiment was done by Ramberg and Snow, and leading already to a limit of in the order of 10 to minus 26. Okay, so this was the first experiment by Goldhaber and Scharf-Goldhaber, and can be also interpreted with a Pauli exclusion principle test. So Ramberg-Snow had a very simple arrangement. So they had a copper strip, an X-ray detector, and the current running through the copper strip. And so usually the current is running through the conduction band, but there's also interaction with the atoms in the copper and can lead to X-ray emission. And they were using a rather simple X-ray detector, so having an energy resolution of about 1 kilo-electron-volt at interesting energy of 8 kilo-electron-volt. So we wanted to do it better. So our principle is seen here. So the allowed transition 2p to 1s, so k-alpha transition in copper. So there would be an empty place for the transition for the electron, and then making a normal transition. Or the 1s state is fully occupied, then it's forbidden by the Pauli exclusion principle. And this energy, the transition energy, is quite different. So the energy shift, if Pauli exclusion principle violating decay occurs, is about 300 electron volt, which is resolvable by modern X-ray spectroscopy. So we are sitting around 8 kilo electron volt with our energy. And you see here, that's a normal transition in copper, K-alpha. And so we are looking for this kind of signal here, which is shifted by about 300 electron volt. So how we are doing this? So the first experiment we did with charge coupled devices as X-ray detectors. I have to say this, we have a big experience with X-ray detection systems, especially with 4pi X-ray detection systems, because we use them also to study exotic atoms in Frascati at the Daphne electron-positron collider. And so we have to use a 4pi geometry not to lose any solid angle. So you see here the effective area of the detectors we are using. So with SDDs, we have a single detector has 100 square millimeters, but we're using 4pi geometry of silicon drift detector, so that we are covering maybe more than 50% of the solid angle. And the energy resolution is around 150 electron volt at 6 kV, and it's a region of interest, maybe 180 electron volt, which is a factor of 10 better than in the experiment by Rambeck and Snow. But we have also a timing performance of the silicon drift detectors. That means we can even use active shielding by some plastic scintillators surrounding the target. Okay, so we have here used for the first experiment with the CCDs a copper cylindrical foil surrounded by 16 charge coupled devices, and these were sitting inside a vacuum chamber because detectors and CCDs have to be cooled to 170 Kelvin by a cryogenic system, and and then we had a readout system. And after about 2 years of running, we got a limit beta square half, upper limit beta square half is smaller than 4.7 times 10 to minus 29. So already maybe 3 orders of magnitude improvement compared to Rambeck's Snow experiment. Okay, so in the 2, we're using silicon drift detectors, though they have a higher resolution. So at 8 kilo electron volt, about 180, 90 electron volt. And they have timing performance. And we are using 4 arrays of 2 times 4 silicon drift detectors, very the quadratic ones. And so with a liquid argon closed circuit cooling to minus 160 degrees Celsius. So, and for the target, we used a strip target, very thin target, about 25 micrometers, and the geometry of 7 times 2 centimeters. So we have a more compact target, which is sitting in front of the X-ray detectors. So, and we have a veto system, so we're using plastic scintillators for active shielding, and also a lead shielding and like traditional shieldings. Okay, so we are using also higher currents for that, so more than 100 amps, and the experiment is sitting below the Gran Sasso, which is the highest mountain in Italy, in southern Italy. So we have a rock coverage of 1,400 meters. So that is a reduction factor of about 1 million in the cosmic ray flux. That is good on the one hand side. On the other side, it also needs that we introduce a calibration source into the experimental system. So we have here tests in the lab made with shielding, without shielding, and so on. And actually, the best situation is giving here is a situation in Gran Sasso that we expect, and it's clear. So the form experiments gave, after about 2 years running, this 4.7 times 10 to minus 29. So this is published, and they want to go better with this. So we are using this arrangement. So the copper target is sitting inside this vacuum box. So vacuum, because we have to avoid condensation of the water vapor around, because we are cooling the SDDs. And we have to also cool the target by water cooling. Otherwise, this thin foils would melt and the target would be destroyed. So this is the arrangement. So here you see inside this target and the detection system with the SDDs, and surrounded by some plastic scintillators to provide active shielding. So the features are, we have here the SDDs. So here an example of these SDDs. It's a 4x2 matrix of silicon drift detectors, and we have the shielding of the rock coverage. And okay, that is really much better than in the first stage of the experiment. So we improved the vacuum system and had employed new SDDs, which we are also using, by the way, for measuring X-rays from chaonic hydrogen and chaonic deuterium at the Daphne accelerator. So we tested the apparatus at our institute in Vienna, and then we transported and installed this system in Gran Sasso. So this system in Gran Sasso is a kind of tabletop experiment. It's heavy because it needs shielding, and that is very heavy. So it's a heavy tabletop experiment. So you see some pictures of installing the two experiments. So inside we have a copper shielding and outside a lead shielding. So it's a line shielding, and inside is this box with a vacuum system mounted. So we increased the current up to 180 amps, which was also challenging, but it's working. So the system is running stable. So we could take data even in the pandemic time. So it was not possible to go so easily to the experiment. There was some safety measures, but it was running nicely. So it took data also in the pandemic time. So we optimized the slow control system before this pandemic situation occurred, and also the shielding. And we can do a continuous energy calibration of the silicon drift detectors, because we have inside the experiment a very low intensity X-ray source. And now we are coming to the analysis. So we are using different analysis methods. And so we are now analyzing the new data set. And also we have discussions with theoreticians for the interpretation of this 2x results, even in the framework of quantum gravity inspired models. Okay, so what we measured. So here you see an energy calibrated X-ray spectrum. So here you see peaks from the calibration source, which is a iron 55 source. It's giving the transition to manganese, giving a nice line at 6 kiloelectron volt, K alpha, K beta. And then we have also some foils of titanium giving these lines. So we can calibrate online our energy spectrum. And here you see the copper peak, which is coming from the background events. So even if the cosmic rays is reduced very much, still after a long time, you see this normal copper peak, which has nothing to do with Pauli exclusion principle violation. So the violating events would sit right here in the region of interest. Okay, so here you see a spectrum without current and with current. So this green line is a fit of the spectrum without current, and the blue events are without current, sorry, and the red ones are with current. So we understand the spectrum quite nicely, and the Pauli violation would give a shift of 300 electron volt from the normal copper line and sit right here. Okay, so where we are standing now. So we reduced the upper limit for the Pauli exclusion principle over time. So you see the here the time in days, and we are sitting end of this year. We expect to sit in the region of 10 to minus 31 for the beta square half quantity. But there's a caveat. So we calculated here the beta square half according to the Reinberg-Snow scheme, which includes a strong simplification. So it is valuable to compare the different results. That's why we used this the same method, but one has to take into account that the electrons do not go strictly through the copper strip. They are doing a kind of random walk, and that's why they have more encounters with the atoms than in this simple model by Reinberg and Snow. So taking this random walk into account, that was also checked by a scientist from Trieste, Edi Milotti. Then the beta square half is much more stringent and leads to a limit in the range of 10 to minus 42. But okay, this is also to be studied in more detail. But you see, we are reaching a very high very stringent upper limit. So let me summarize. So the VIP2 experiment follows an experimental concept introduced by Reinberg-Snow about 20 years ago. The big advantages are the underground laboratory of Gran Sasso and the good X-ray detectors tested also for exotic atom research. So silicon drift detectors are very nice detectors for 4π installations of X-ray spectroscopy. And the VIP2 after our first experiment is set up and running with many improvements. Okay, if we find a violation effect, then I would say then we have a lot of work in checking our apparatus. So you know this story about finding the violation of the speed of light in vacuum. That was a a big point. Okay, so the cooperation with theory is extremely important. And Antonino Marciano from Fudan University is working on quantum gravity models. And due to the very high sensitivity of the Pauli exclusion principle tests, he is pretty sure that one can test also these models with the findings of our experiments. Okay, so if you want to read more about our experiment, I can give you this reference. So this was published in CERN Korea in March 2018. So putting the Pauli exclusion principle on trial. And so you can find more about our experiments in this paper. So, okay, there is a Lefaucoun also looked in the case of Pauli exclusion principle and said the special place enjoyed by the Pauli exclusion principle in modern theoretical physics does not mean that this principle does not require further and exhaustive experimental tests. So unfortunately, Lefaucoun died, but I think this statement by him is still valid. Oh, hey, died a little bit early, but I wanted to close now, and we are preparing also with more stringent tests to test the quantum gravity models. So there's related with Lorentz symmetry breaking at the Planck scale. You cannot so easily reach the Planck scale in accelerators, you know, but with some experiments with high sensitivity, you can even test some models. Okay, so I thank you very much for your attention.
So thanks, Johann, for this great talk. And we give you internet claps. So let's open the microphone for questions. If someone has a question, please announce it here in the chat. I have a question, which is related to why do you have to cool it down? Because you have to shield this device and you have to keep a certain temperature, right? But the question is, by doing that, you are going more and more into the quantum limit. So why would you expect to find a violation of the Pauli exclusion principle in the quantum limit? What happens with the coherence? Shouldn't we expect a violation by tending to a classical limit? That remains puzzling for me because the Pauli exclusion principle seems to be robust against the coherence, right? Because you can hit something, but I still believe that the Pauli exclusion principle is still valid. So do you have a take on that? What do you think about that? It is intriguing for me.
Okay, I have to say that the experiment itself is more classical. It's classical. So we do not prepare quantum states and so on. Yeah? Would be also interesting to have experiments, for instance, and it's already done in quantum computing. So preparing states and looking if the Pauli exclusion principle is fulfilled. But our experiment is a classical experiment, X-ray experiment. So we do not care about the coherence and so on.
Yeah, but I was wondering, because you fix a particular temperature, right? You say something like 163 Kelvin, but would you expect something different, but by going to a lower temperature? I mean, or it is a meaningless question. Is it a meaningless?
I would suggest that it's macroscopically, it's classical. So we have to use these temperatures for our detectors, but not for the experiment itself, for the idea of the experiment. So we have to come down with the energy resolution. That's one point. And because if you're sitting at higher temperature with the X-ray detectors, you have a lot of shot noise. So your signal will be covered by noise. And to find this probably very small effect, if there's an effect, you have to go to lower temperature, but not for the quantum regime. It's a macroscopic.
Yes, I see. So yes, so you basically low down the temperature of the detectors, but not of the system you are detecting.
Yeah.
But okay, yes. So your answer is that you wouldn't expect any difference if you cool the system down. So if you make it quantum, I mean, or, no.
I do not expect in this kind of experiment. So as I said, if you have experiment with single ions or trapped systems prepared for quantum arrangement, then certainly decoherence plays a role, and so you have to avoid decoherence, and you can check with this very well prepared states the validity of the Pauli exclusion principle, which is already done by some experiments. So, and giving also negative results, but the limit is not so high.
Okay. Well, are there any other questions or observations in the room? Please write it down in the chat. We have some time. So if we don't have any more questions, we thank again Johann for this wonderful talk. Thanks, Johann, for being here with us, at least virtually. It's great to see you again, at least in the computer screen. So